Good afternoon, everybody. Welcome back to lecture number 43. Today we will explain few concepts. The first concept is the comparison between the torque. In a nutshell, if you distribute the windings across more than a teeth, you're going to get a higher torque compared if you concentrate it in one teeth. Yes, here the flux will be higher than each individual tooth. However, the issue here is the reluctance created will not be strong enough compared to the reluctance change created in this machine. So always a good strategy is to ignite more coils every time to get higher torque. And this is actually demonstrated in the half step. Here we have higher torque. Here we have higher torque because we have two coils are active. If I ask you in the test, can you get, this might be a question in the exam, can you develop a lookup table for a 30-step full step operation with stronger torque compared to this one? Yes, you can do. You just need to add one here, etc. Okay? You need to take a half step, this 1545, and swap it up. So you should start from here, 110, 011, 101, etc. This way you can get full step and high torque. This might be a question in the test. The other concept I want to talk about is the permanent. So as you can see here, compared to same number of phases, this is can deliver higher power. Okay? Actually, this is high, but this is higher. So this one torque is higher. Well, the power is the same, but the torque is higher.
What actually torque?
You're right. This is the torque here is larger. Okay? Then the other type is what did I tell you about the other type? Can we insert here the rotor? Does it have anything or just steel? Steel. Can I remove the saliency here and replace it with inner magnets? So take for example this shape. Here I'm going to have a round rotor, but I'm going to insert north and south pole actual magnets. Actual magnets. This way, what should I worry about? Here, previously, I did not worry about the polarity of the rotor. Because as long as I have a teeth here, it will be guided, aligned, based to adjust the reluctance. That's why we call it variable reluctance. But if I have a magnet, I'm going to have a north and south. Every magnet should have a north and south. I really need to plan the alignment between the north and south. And usually the alignment should be, if the rotor is north, if the rotor is south, the stator coil should be power to be north. Okay? But before that, how coils are wound using permanent magnet stepper motor. One of the most well-known permanent magnet stepper motor consists of 2 phases in stator and 6 poles on the rotor. This is a very well-known structure. 2 phases in the stator, 6 poles in the rotor. Now let me ask you a question. When we say phase, do we mean AC, A, B? Or do we mean the same DC fired at different times?
Same DC.
Same DC fired at 2 different times. Remember, this is not an induction machine. This is stepper motor is a snapshot. You connect the DC at certain windings. So each phase is wounded on 2 teeth as shown below. For example, you might get teeth number 1 and teeth number 2 are sharing A and then half of the coil, the other half to B. Here, what's the advantage? This is a different source. A is different source than B. صح ولا لا? If A is on, B is off, using what? How can I make A and B on or off?
Power electronics.
Using power, if you don't know, using power electronics. I connect teeth number 1 halfway through that coil. So now the current would flow using this direction. And then it will go here, back. Clear?
Yes.
If I make B on, A off, I'm going to have a different direction, but the other half of the coil. Basically, every coil should have this half coil should have a unique direction. This half coil should have a unique direction. Same for A and B. Should be this way, should be that way. In other words, this half coil always away, this half coil always in. The other type of connection, this is unipolar. Because I can only create the same pole, it has to be, this one always has to be north. It cannot be south. How can I make it south? If I reverse the direction. So if I connect the 1 to A and B, okay, I'm going to have current flowing either this direction or this direction. So this is bipolar. If I move the current in the away direction, what will happen? The flux will reverse its direction. So if I connect from, for example, if I connect, I think this is a typo, this should be 2B. This is 1A, 1B. If I connect it this way, no, hold on a second. I will show you how to do it using power electronics. Maybe it's better. This is the power electronics. Here, the unipolar, center tap, common. I connect 1 to phase A using power electronics. The other coil, I connect it where? To the returning path of A. Okay? The other 2 coils, I connect them to B. So if I ignite this, the current will go, for example, only unidirectional. كده. وهذا current will go unidirectional. فdepending if A or A prime is connected, I'm going to have a flow. طبعا هنا they name it differently. ال A prime هي ال B. Okay? The other one, the full, it means coil A should cover, coil A should be connected completely unidirectional. The current can go back and forth using the power electronics. Okay? That's the idea about this. Is the bipolar, because the whole coil can have 2 different or opposing directions. Tamam? Let's see how that operates. For a unipolar full step operation, if I have 1, 0, 0, it means 1, 0, 0, 0. And this is what north. If I activate B1, this is B1, the south would align with the north. So I'm rotating 30 degrees clockwise. Activate the other phase, which is A2. This is A2. What will happen? I'm going to align this south to this north. The last step, B2 activated to 1, so I'm going to a 90-degree rotation. This is the unipolar.
This is for 8 poles or 4?
No, this is 1, 2, 3, 4, 5, 6 poles.
No, I mean for the
4
stator.
windings.
It's okay, but didn't we take it to be 8 before?
2 phases in stator and 6 poles in the rotor. So this is two phases. 1, 2, A and B. But the difference is the current flow direction. Tamam? Here A1 and A2, they are different. For example, here they follow the same coil will only experience unidirectional movement. You cannot reverse the direction. But the other one you can go back and forth. But don't worry about the naming, worry about the tables, okay? Worry about the tables. The unipolar half step, what's the difference between half step? I have two poles north at the same time. So I add a middle step. So 1, 0, 0, 0, I keep the one, add one here, and then remove the one. This way I can move only 15 degrees. And again, what is the disadvantage of the half step? The torque. The torque is having ripples. We explained last time, the torque will look like that. If you have two coils active, you will have higher torque. One coil active, you will have a less number of coils. This is the disadvantage. Okay? Also for the bipolar, what's the difference between bipolar? A1 is north, A2 is south.
A1 is north, A2 is Yes, sir.
A1 is north, A2 is south. So you start with north and south. Okay? Now, from the beginning, for bipolar, I have two coils active at the same time. But they are in opposite direction. They are in opposite direction. So if you look at this cable is really not important. I'm being clear with you.
دكتور اساس كلاريفاي الازرق بالنورث صح؟ لا
الأزرق north, الأحمر south. Okay? If you have it bipolar, you connect 2A and 1B to the same coil, 1A to 1B. I think it's a typo. However, the naming here, A or B, they are different, okay? And here we connect terminal 2, tooth number 2, and tooth number 1. 1 to A, 1 to B. So I think this should be 2. I don't know. I think this should be 2. 2 to B, 1 to A. Then the same coil will flow the same current. The last one I want to talk about, and this is a permanent magnet is not that important compared to variable reluctance, because what's the issue with permanent magnet machines? They will demagnetize, and you don't want them to be demagnetized. For continuous operation, it's better to have variable reluctance. Okay? For bipolar permanent magnet half step, the same story. You're going to have north, nothing, south, nothing, north, north, south, south. So here, 4 coils are on at the same time. 1, 2, 3, 4. 4 are active at the same time. Same thing here. S, N, N, S. How to do it is replace every N with 1. It will be similar. And then add some zeros for steps that are 30, 60, 90. Okay? So try to understand these tables. You cannot memorize them. They are lengthy. Here, for example, you have 24 cases. Here you have 12 cases. Here you have 24 cases. Here you have 12 cases. And previously, how many cases do you have? Here you have 24, 12 cases. 24 and 12 cases. So focus on how to construct these tables and those basic equations, okay?
Doctor,
Yes.
what if you want more precise, up to 1 degree or 2 degree? Or, because I
You have to
understand
increase number of teeth. Either in stator or rotor. No, you have to make, use this formula of designing.
Because
this formula.
stepper motors, we use
Use this formula for design. NS minus NR over the multiplication. So pick a number that gives you the angle that you want. And my advice to you, always go to the standards of the machine. There is a prohibited combinations. Some of the combinations are prohibited. They would create resonance. Remember the resonance issue? We had resonance issue. One of the disadvantages is resonance. So you have to go back to the standards and pick the right combination if you want to go smaller steps. Okay? So this is pretty much the permanent magnet. Some comments about it now, I have to indicate that these comments are for the unipolar, okay? This is only for the unipolar. To reverse the direction, the sequence of pulses has to be changed from A1 to B1, A2 to B. You start from B1, A2 should be B2, A1 should be B2, and then A2, and then B1. Okay? So from A1, B1, A2, B2, it should be A1, B2, A2, B1. So how did we do it? B1 should be at the end. Swap B1 and B2, and swap A2 with A1. Clear? Swap A1, keep A1, B2, swap B2 with B1.
Swap the B's.
Swap the B's, okay? For the full step operation, only one half coil is energized at each step. Half coil is energized. For your unipolar, we call this as a half coil. Only one is energized. The current is flowing here, or the current is flowing this way. You cannot have them both on at the same time. For the bipolar, you can have the movement either from B to A or from A to B. This is unipolar. The changing direction of the flux allows you to have one time this to be south, the other time it can be north. Clear? واضح? Unipolar would change its polarity. This south, this is north, now it becomes south. Because the flow of current is opposite. That's what you need to know. The torque produced by the bipolar is higher. Why? Because we are utilizing more coils. It's very simple. If you use more coils in a machine, you expect the torque to be higher. The torque produced by half step is pulsating type. Same. For a half step, always it has ripples because one time you have two coils, one time you have one coil. Two coils, one coil. If you want to have uniform, smooth stepper motor, never ever use half step. You have to use full step. So that might be a question in the test. I want to have a very smooth stepper motor. Should I use half step, full step, third step, A or B? What's the answer?
Full step.
I want to have a pulsating motor.
Half step.
Half step.
Okay? So let's look at the power electronics. Try to understand the power electronics because this is what matters. If you buy a machine, so as an engineer, you should really have the ability to analyze the power electronics curves. So what is this device?
MOSFET.
It's a MOSFET. So you need to look at the MOSFET types. And why this diode is put?
Protection.
For protection. Same for this diode. Look at here. This is the supply. How many supplies do I have? 1, 2. Can they be the same? Yeah. They can be the same. This is V plus, this is V plus. This is the ground. So the whole system is built on DC. So you expect this to have a DC bus. This DC bus, if you want to create it, you have to use rectifier from the inverter. So you expect to have from single phase rectifier, then you have the 24 volts to 100 volts, 700 volts, whatever. You connect the diodes, you have to check the ratings of these diodes, how much they can forward and reverse current. You have to check the capability of every MOSFET, and you have to check what is the input, what is the pulse needed from the microcontroller to trigger the gate. So as an engineer, you really need to come up with a microcontroller that is capable of driving those MOSFETs. Let's see the operation. Here, what do you see? This is unipolar or bipolar?
Unipolar.
So unipolar, it means only half coil is allowed. Only half coil is allowed in the operation. Let's go back to the table. Let's see the unipolar here. 1, 0, 0, 0. So A1 is 1, 0, 0. So where is A1? Go back here. This is A1. So I have 1, 0, 0, 0. If this is 0, it means this is off, off, off. So I only have this to be connected. So how my circuit would look like? My circuit would look like, would look like this. Okay. بعدين يروح وين؟
الكويل.
What's the direction of the current?
تمام. يروح.
يروح للcommon. Okay?
Yes.
So if it goes to the common, it will split to here and here. Would the current be connected here? Will be?
No.
No, because?
It's not triggered.
Wrong.
No, it's not triggered. This is open circuit. So if this is open circuit, the diode will be off. Clear how to analyze it? So now I don't need to worry about coil B. So I only know my operation is I'm now connected to the high voltage coil. So this is V supply, V supply. This is a point of common connection. This is what we mean here. Unipolar. This is only active. Everything else is not active. Same story. Can I go to 1, 0? Can I have 2 active? Remember the half step. Can we do half step? Yeah.
Yes.
If we do half step, I go back to the same analysis. What's the half step? 1, 1, 0, 0. So this is on. Again, this is on. If this is also on, what will happen? These 2 coils are on. Again, they go back to the same common connection. So those 2 coils for half step, they are on. Go back to unipolar half step. No, my bad. It's B1. I'm sorry. B1. We made a mistake.
You said that it's only half coil, right?
Yeah. Go to B2, B1. I'm so sorry. Go back to B1. If you go back to B1, only half coil. So can we connect to the same common point?
Yes.
Yes, we can connect to the same common point, which is tied to the supply. So this coil is on, this coil is on. Okay?
We will have 1, 0, 1, 0, صح?
1, 1, 0, 0. The second column هو البي مش الA. Okay? Clear?
Yes.
So I want you to go and analyze these tables and see if they make sense or not. The unipolar, I need how many transistors here? 1, 2, 3, 4.
You need 8.
I need here 8, which is more. So use the same combination. Here the control is a bit more challenging. But remember, here what do I have? I need to have 1 coil to be north. Okay? 1 coil to be south. Go back to the unipolar. Bipolar. So A1, A2. How to make it?
Full Q1 or Q5 or Q6.
Let's start with the simple approaches.
1, 1, 0.
Q1. Oh, the control here مش على الترانزستور. The control I'm giving is على الكويل. طبعا this is a little bit.
بس البلس رايح لل Q1.
No,
Q1 will be on.
No, it's not that way.
Q6 will be on also.
So the thing about it, yeah, Nawaf, is for bipolar full step operation, what do you need to do? You need to have A1 and A2, one is north, one is south. For unipolar, how is this connected? 1A here, طبعا هنا بمشي على السلايدات, I assume إنها it's correct. هنا 1A, واحد على B. So one is connected to على A, one is connected على B. So it means, طبعا هنا you don't know the clock, but my point is you have to make one moving from positive to negative so that you have a north. The other one should be from, the current should be flowing from negative to positive. So depending on the direction of the coil, you choose the IGBTs.
نقدر الأربعة.
Yeah, but both of them, they have to be operational. Clear?
هنشتغل 4 المفروض.
Yes, 4 at a time. That's correct. But this way, 1 and 5, 7 and 4. To have the first row. 1 and 5 will give you current going here. The other one, I want the current to be reversed. So I pick 7 and 1. Okay? Now this is too much details. Yani there is missing parts. There is, okay, where this is tied to in terms of the teeth. So this is not easy to explain. And this is the end of module 5. This is the end of module 5 where we have covered universal motor, Single phase induction, we talked about the types of capacitor. We also talked about what? The stepper motor. Did we talk about the reluctance? No.
No.
So try to learn. If you want to learn machines, if I were you, I'm going to go ahead and jump to reluctance machines and just study them. They are easier to understand. They variable reluctance, easier to understand, and they are now the future. So once you master them, you can step back to the classical one. That's the best way to learn machines. You cannot learn all the machines. People become experts in one or two types of machines. And you really need to improve yourself using the power electronics. Okay? Now, let's start the last module. What? What's the issue?
باقي واحد يكتب.
Yes. No, there is a last module and there is one paper I want you to study. The last module is a paper. And I'm thinking about maybe I'm going to let you study one of the journal papers and then we're going to ask questions. Yes? Probably I will highlight where I'm going to ask. Okay? Is them camera شغال? So variable speed drives, VSDs. This is how they look like. They're cabinets and there is a local controller. This is, we call it local HMI. Shutdown, emergency buttons. This is another type, how they look like, the drives in real life. So we're going to start about modeling of induction drives using reference frame theory. This is the first lecture we're going to talk about today. And this lecture, I'm not going to ask about details, I'm going to ask about the general picture. Okay, we're here more into learning. If I want to take, if Nawaf goes and take machines course at University of Washington, inshallah, then this module would give you a little bit step, extra. So when you go to the class, you're not lost. My first ever lecture when I went to my master's program was machines. And I ended up doing machine. Yeah. Okay? So this is prepared by Dr. Abu Bakr Salim. Now let's go back to the electrical drive system. We have been talking about motors. The whole red box is called the drive. The drive has 4 components: motors or machine, sensor, controller, and power electronics, or power converter. This is very important. When you develop a document for your company, if you work for Qatar al-Riyadh, and they have machines in the metro, they have machines. I am pretty sure they were talking about the drives of the machine. So always look at the motor drive to be the link between the mechanical and the electrical. Now we are expert in the machine, but we are not expert in controller, on sensor. We are not going to cover it here because this is mainly usually ready material. Speed sensor is ready, controller is ready, you just need to program it. But the power electronics is covered in E460. We will touch a little bit on it. Modeling of induction machines using reference frame theory. I want you to learn what is reference frame theory. To me, it's more important than the power electronics. Now, do you remember the E360 or single-phase machine rotor circuit where we have the slip?
Yes.
So this is a huge problem because every time the speed changes, I'm going to have a new circuit. Is there a way I can change my reference such that instead of me standing on the stator, can I stand on the rotor? Yes. We call this the rotor reference frame. Can I stand on the 60 Hertz rotating RMF? This is, we call it the synchronous reference frame. Can I go back and stand on the stator? Yes. We call this the stationary reference frame. Can I have another random reference frame? We call it the arbitrary reference frame. So I have two possibilities of references. Either stationary, either rotor, either synchronous, either arbitrary, random, something else. Maybe the speed of the vehicle, maybe the speed of the space station. So the motor has inductances that depend on the frequency. It's not only the slip, the frequency. Every X has 2 pi F. The rotor current has a different frequency than the stator current. So if I change the supply, if I change the drive, you add a miss on top of a miss. If I do V over F control, I have to redo every control, I have to have a circuit. Every control, I have to have a circuit. And to have a circuit, I need to go to decide back about my controller. So due to rotation of the motor, changing the frequency of the supply, and other factors, reference frame theory is used to simplify the mathematics behind the induction machine. We're going to see the craziest math that you will ever see in your electrical engineering. The idea of using reference frame is to refer the parameters that can be seen as constant values as much as possible to simplify, Similink, etc. So why it's used? Because we want to eliminate rotor position dependency for the inductors or capacitors. If you have single machine, has capacitor, single phase.
Yes.
Transform nonlinear system to linear system can be used to make AC quantities look like DC, even though they are. So if I go to the synchronous speed, the circuit, if I change the electrical frequency, it will be the same. Because I am tied with the frequency of the supply. That's my reference. Framework for most controllers. We want to have framework of every controller. This is very important in reading the manuals. So the air gap flux is moving with synchronous speed. The RMF rotating at what? RMF rotating at 2 pi 60. So I can have synchronous reference frame where the observer is assumed to be moved with the synchronous speed of electrical frequency. Or rotor speed. As long as the rotor is moving, I'm tying my reference to the rotor itself. Or stationary, where we're used to observe on stator frame itself, which is stationary. Stator is always stationary. So here's some history. Reference frame theorem, they started in 1929 with Park transformation. What's Park transformation? For synchronous machines, they use rotor reference frame. But for synchronous machine, isn't the rotor rotating as same as the synchronous speed?
Yes.
Yes. So you can also call it synchronous reference frame. So for synchronous machine, the rotor reference frame equal to synchronous reference frame, because this is what? A synchronous machine. Then Stanley, for induction machines, he came up with stationary reference frame, because induction machines were invented after synchronous machines. Tesla was in between. Krohn, induction machine, he used synchronous reference frame. That's another step. Brereton, for induction machine, he used reference frame. And then Krauss, in 1965, he used arbitrary reference frame. Arbitrary يعني عشوائي, generalized reference frame. With anything you can. So stationary and rotating reference frame. Let's talk about. So this is the sinusoidal signal. It rotates, if you want to have it as a vector, it rotates at this speed. You're familiar with this shape, صح?
Yes.
Physics 102, or Math 002. Now, if I have RLC circuit, E213, or maybe I think E201, lagging, leading, etc., you're familiar with them, right? Now, if I want to have the two phasors, let's say this is current, blue is voltage, red is current, so current is lagging the voltage. So current is lagging the voltage. It chases the voltage. This is what we call the phasor representation. If we multiply it by e to the power j omega t, then we will end up getting those arrows. And the real projection of it is the sinusoidal. The real projection, no, not the real, the imaginary axis protection. هنا imaginary الأزرق واحد صار واحد. Imaginary protection 0 صار 0. Remember this. Okay, this is very conceptual. For three-phase representation, I have the three phasors rotating at 60 Hertz with 120 degrees apart. The question is, why this is not rotating? Okay. So, the question is first, can I convert the three phases, blue, red, and green, into two equivalent 90 degrees alpha and beta? Yes. If I just multiply them by a certain matrix. Do you remember in Math 002? Or I think Math 101, do you remember? Or the linear algebra, something we call the rotational matrix. Do you remember rotational matrix? It had something that cosine of theta, sine of theta, something like that. You multiply it by a vector, and this would rotate your vector by 90 degrees, or by theta, whatever degrees. Do you remember that in math?
Yes.
Do you remember the rotational matrix?
أذكر في شيء زي كذا.
Huh?
أذكر في شيء زي كذا بس ذاك لا.
Okay, you did not. You were studying from the slides. Those who studied from the book, like Nawab, they remember. So the idea behind it is we have alpha and beta. I can convert the three-phase signal using a transformation. This is what's the size of this? 2 by 3. What's the size of this? 3 by 1. Then I'm going to have a 2 by 1 matrix. It preserves the characteristic. By the way, this is machine learning. Who's working on machine learning? You?
A bit.
So are you familiar with transferring data from images to vectors? So same for machines. Can I transform the information from ABC to another two-dimensional quantity? And then I can get it back later. But it's easier to do the math here, do my transformation, do my controller, do my V over F, and then I can get it back. And I will show you how this looks like in models. So for the synchronous reference frame, instead of having those three vectors, I can replace them with two vectors that are 90 degrees apart. The light blue is the equivalent vector, is the summation of the two vectors. Note that the blue vector is the same, so it preserves the characteristics. How to do this transformation? Do you remember we did example in the single phase machine where we ended up having 2 over or 3 over 2 cosine, etc. What did we do? We did multiplication, expansion of cosine and sine. Here I multiply, this is 2 by 3. Okay, the dimensions here wrong. This is the correct dimension. If I multiply by a constant, the currents A, B, and C, with a matrix of size 2 by 3, this is the 3 by 1, so I'm going to end up with a 2 by 1 matrix. And it has 1 cosine gamma, cosine 2 gamma, 0 sine gamma, sine 2 gamma, where gamma is 60 degrees, 2 pi over 3. Is it 60 or 30?
2 by 3.
Yeah, 60.
2 by
أو بدل باي ب 180 360 على 3 كم؟
120.
120. Okay. So this is no. Is it 120?
2 by 3 هذا 60.
Whatever. It's 2 pi over 3 radians. Now the other version of it, basically if you plug the numbers here, you multiply it by a constant matrix. 1 minus half, 0, square root of 3. I think this is 60.
أنا شوف الكوساين ماينس. كوساين طلعت لك ماينس.
Reference 60.
Okay, yeah. Okay, that's gamma is 120. So cosine of 120 is minus half. Cosine of 2 times, and that's 240. So this is what we call it Clark transformation. There is something called power invariant, where you just multiply by square root of 2 over 3 at the beginning. This would preserve the power. This would preserve the power. So you have two transformations here. I wanted you to know them. So I have I, the current. It has A, B, and C, 3 phases. Now can I have them as two quantities, alpha and gamma? Yes. The other one is the rotating frame. So this is the first transformation is we transform to synchronous reference frame. Because I put gamma here to be 120 degrees. So I get a three-phase now, they are alpha and beta. I take alpha and beta, I do another transformation to them, which we call Park transformation, where I get them in the rotating reference frame. So I take the alpha and beta, multiply them by another matrix that has this is a rotational matrix, nothing but rotation matrix. Cosine, sine, minus sine, sine, of a theta. What is theta? Is my rotor position. Rotor position, okay? At the end, I'm gonna have the two vectors to be constant. They're sync with the rotor. Here الأزرق والأحمر they change.
Yes.
But الأزرق والأحمر, dark blue, red, they are fixed. They are constant numbers. And this is what we call the DQ transformation. So DQ transformation is two transformations. You get a three-phase, you multiply them by alpha to get them alpha and beta. After you get them into alpha and beta, you do another transformation, which is called the rotating frame. It's a rotational transformation, where we align both axes to be the same. So we will continue next lecture here, okay? We may need an additional lecture on Wednesday. Let me think about it, okay? Any other question? So I want to show you the math, how the math is hard. Huh?
Some scary stuff.
It is very scary. If you go to grad school, this is what you will have to program.
مو كأنه الماتيريال طال شوي.
It has to.